Okay, to refresh from the last video, when we measure substrate to product conversion in the presence of an enzyme, we see something like we have on this page. Starts with zero product at the beginning of the assay at time zero, and it goes into a linear production of product as a function of time, and then it levels off when we run out of substrate. You can't make any more product if you don't have any more substrate. It's this area right here, the initial slope or initial rate that we're interested in. That's a linear velocity that we measure over and over again in these types of experiments. Okay, let's show you what we can do with this in a way that's going to be very powerful. It's going to be very difficult to understand this as well, but bear with me, this is an important area. We are now going to measure velocity over and over again at different substrate concentrations. The one thing we haven't mentioned is the units here. The units for velocity are going to be micromoles of product per time, such as second or minute. And the substrate concentration will typically be in millimolar or maybe micromolar. Micro looks like a kind of a U with an extended part coming off of it. Those units will come back and be something that we look at a little bit later. Now I'd like to show you what a Michaelis Menten plot looks like. This is also called a direct plot sometimes. And that's because we measure velocity and plot it directly as a function of substrate concentration. Now I'm going to put a bunch of dots on here. Each one of those represents a velocity or a slope in an assay like we showed you on the previous page. So let's take a peek. First of all, if you have no substrate in a reaction, you can't make any product, and therefore you can't have any velocity. So just like on the previous page, 0, 0 is always going to be one of our points. Okay, now let's say we do put some substrate in, some low concentration of substrate, and we get some velocity like that. Now if we put twice as much substrate in there, the velocity will be higher. The substrate's going to bump into the enzyme more often, you're going to get more product. But here's the interesting thing. Twice as much substrate does not give twice as much velocity. If you triple the substrate concentration, you won't get triple the velocity, so on and so forth. What we end up seeing is something that looks like this. I'll try to connect the lines a little bit here. What we can see is that we increase substrate concentration, velocity increases, and eventually levels off at some maximal velocity. In fact, I want to make a note of that. Where it levels off is the velocity that it can't go any faster. Think about if you're measuring how fast a car goes. You put the gas down on the gas pedal and you go faster and faster and faster, but eventually, no matter how far you're putting the gas on, it can only go so fast. That's the maximal velocity we have here. Now, before we say anything further about this graph, I want to make a note about its shape. Its shape is something that we have seen before. Let me say it this way. We start at 0. You start at some slope, and the slope gets lower and lower and lower and flatter until it tangents at some maximum. Do you remember what we call that? This is called a hyperbola. We saw that in our last unit when we talked about how the oxygen saturation curves for myoglobin were hyperbolic. That is, for non-cooperative binding to oxygen, we saw a hyperbola. So we're seeing that same thing again here. And that's not a coincidence. There are some similarities between those two systems. Now here's another similarity that we can talk about. What if we took that maximum right there and we went to its half maximal or 50% maximum and drew a line over to our curve and then drew that down to this axis. Remember that? In our oxygen saturation curves, we define that as P50. That's not what we call it here. This is going to be called the capital K subscript M, or Michaelis constant. Now, let me just add again that it comes from the 50% mark. That's 1/2 Vmax right there. And like I said, we draw over to the curve and down. The Km is on the x-axis there. It's a point on the x-axis, or it's a point on the substrate concentration axis. Okay, let's define a few more things on this page and leave it at that for this video. First of all, let's take a look at this equation over here. What this equation is a y-axis, that is velocity, as a function of an x-axis, that is substrate concentration, with two constants, Vmax and Km. We've already defined those on our curve. So if we plot velocity on the y-axis as a function of the x-axis, we can determine Vmax and Km, and this will be a hyperbolic curve. That's what this equation is. It's a hyperbola. This is called the Michaelis Menten equation. And we will revisit it later. Up to the top of the page, we have what's called the Michaelis Menten model. And this goes as follows. If you take an enzyme and a substrate and mix them together, they form a complex. E.S is the Michaelis Menten complex. Keep using those two names over and over again. Once you form this complex, the dot means it's just a hand-in-glove substrate bound to the enzyme. Nothing's happened yet. Eventually, though, the substrate, once it's bound to the active site, is going to become product and get spit out, and you're going to end up with the empty enzyme and a product. So we have great use of this Michaelis Menten model because we can look at the two sides of it. When E and S come together and S fits in the active site, but no chemistry has occurred, this refers to binding, which is really all about specificity. Which substrate is going to bind is the one that binds better, like a hand in a glove. This side, when we take substrate to product, after the substrate is already bound, has nothing to do with binding or specificity. And this has to do with chemistry. That is catalysis. Now, do you like how we did that? We've brought this right back to the dual nature of enzymes. And we're very interested in using kinetics, the curve we have below, to describe both binding and specificity, and chemistry and catalysis. And we'll show you how we do that on the next video.